For my Lab 2 of motion of a falling object, I tested Newton's second law when F net is not equal to 0 by dropping a paper ball and calculating the velocity, and then plotting them on a graph and taking into account outside forces, like drag force. Overall, my experiment followed relatively close to the model line. Again, I dropped a paper ball of mass 0.00225 kilograms from a height of 1.74 meters. I knew this height because I dropped it from the same height as me. I then used tracker's point mass dots to click the center of the ball at every frame throughout the clip. From this I obtained my graph by adjusting the axes to have the ball fall down the negative x-axis. After, I was able to obtain my initial velocity, which was 0 meters per second, because there is no velocity when the ball is dropped from a resting position. I also obtained the final position, which will be helpful later on when trying to calculate the constant and the drag force. Next, I used the data I collected and plugged it into VIDLE. I changed the mass to 0.00225, the initial velocity to 000 because the axis is started where the ball is dropped, and the initial ball velocity is also at 000 because it starts at a resting position and the experiment begins at t equals 0. Next, I had to change delta t to be a very small value, so I used delta t equals 0.001. The Earth's magnitude of gravitational field is 9.8, and I left the j hat equal to the vector of 0, 1, 0. The value I got for my constant b was 0.001518. I calculated the b constant by simple trial and error. I had to insert different values until I calculated the final position matching the actual final position. My b value that I found was b equals 0.001518, and the final position from VIDLE was 0, negative 1.683, 0, which matched the final position in tracker from the experiment. Then, with this constant, we're able to calculate the drag force. Then within the while loop, I put t is less than 0.7 because the time it fell only lasted 0.7 seconds. And then the weight force is calculated by negative ball mass times gravitational force times j hat. Then the drag force Fd was calculated by the equation negative b times the magnitude of the ball velocity times ball velocity or velocity squared. And then F net is the weight force plus the drag force. And then I used Newton's second law to calculate the new velocity and then the new position. And then I went through this again on the while loop until t is greater than 0.7. And this is the model I obtained when I ran my code. My data to compare the model position versus the experimental position, with the model represented by the red line and the experiment position represented by the blue dots. As you can see, this experiment follows closely to the model and almost exactly the same in the beginning, and then starts to deviate. It goes under the curve because my b-value was too low. Another source of error is when I was using tracker, the ball fell, it became blurred, so I tried my best to estimate the center of the ball, but there's always room for error. In conclusion, we are left with two questions. First, what does it mean? When examining the velocity versus time models with and without drag, the model with drag predicts the terminal velocity because the terminal velocity is reached with F net is 0, or when the weight force is equal to the drag force. If there is no drag force, then the terminal velocity cannot be reached and the object will continue to increase in speed. The second question is what if? The what if question challenges us to think if the terminal velocity would change if there was an initial velocity not equal to the 0, for example, me throwing a paper ball versus letting it drop. Like mentioned before, the terminal velocity is when the object has 0 acceleration, when the weight force is equal to the drag force, and therefore our net force is 0. The terminal velocity would be the same because even if the object starts out falling at a greater velocity than the terminal velocity, it will slow down until it reaches the terminal velocity.